extract as much as we can, right? So we already have a probability distribution, right? So let's do some statistics. Let's do some stats, because we already have the probability distribution, right? So it's 2 over L sine squared k sub n x. And we already discussed. So this is the first state. So this is the ground state, n equals 1. So if you look at a probability distribution like this, what does it tell you? It tells you that if you prepare a particle in this state, okay, so you have a bunch of experiments, you prepare them all to be in the first ground state, and then you start measuring away. You measure position, you get a value here. You measure another position in a different experiment, you get a value here. You go to the third lab, or to the third experiment, you get a position here. Fourth, you get a position here. So you get accumulation of position measurements. They will be clustered around this maximal point. Some will be here, some will be here, but most will be here. That's what this probability distribution means. It's important that in each of these, you do that in a new experiment. On the other hand, if you measure position, you get a value. Then when you measure position again, you will get a value that's governed by a different distribution. We will discuss that. That's very important. For now, just trust me that it's important that you go to a fresh new experiment every time. So you prepare, it's almost like cooking. You prepare 1,000 experiments, you prepare 1,000 particles that are described by psi1. Then when you go to the lab, you measure position of the first particle, you will get a value. You measure position of the second particle, you'll get a value. Then you collect statistics, and if all of those particles were in psi1, then the statistics, the histogram, will look like this probability distribution. That's what it means. Okay, if you have psi2, on a different day, you prepare 1,000 particles in state psi2. Okay, and then again, you go ahead and you spend the whole day measuring position in each one of those particles, right? First particle, you measure position, boom, you get a value. Second particle, boom, you get a value. Third particle, boom, you get a value. Okay, each time you're measuring position on a particle in state psi1. So you prepare a bunch of particles, they're all in state psi1, and then you measure position on the first particle, you get a value, you leave that particle alone. You go to the second value, it's prepared in state psi1, you measure value of position, you get a value, you write it down, you leave it alone. Okay, and you're gonna get an accumulation of position measurements, and that would look like that. Okay, so this is L over 2, this is L, this is L, this is 0, this is 0, and so on. So your histogram will match this probability distribution. Well, we can do statistics. Let's just do some statistics. Let's calculate average x. Okay, by definition, average value is x times p of x dx. That is 2 over L, I can take that out of the integral, times x times sine squared k sub n x dx between 0 and L. It's L squared over 4. So x bar is 2 over L times L squared over 4, which is L over 2 quantity squared. You get L over 2, which says that the average position is in the middle of the box. Well, that's obvious. Look at these distributions. They're all symmetric about the center of the box, L over 2. So does this result make sense? You should always go back and see, does it make sense? Does it make sense? You should always reflect. You should never just write down and just hand it in. I know the result. It's for you. Okay, so does it make sense? Yes. Okay, average is in the center of the box because all psi sub n squared, i.e. all p sub n are symmetric about L over 2. Well, that makes sense, right? Let's just continue. Let's calculate the average of x squared. Not the square of the average, but the average of quantity x squared. Why? You will see in a moment. Like, why would we want this quantity? Probably because we want standard deviation, right? So let's do 2 over L between x squared P7 of x dx between 0 and L. That's how you would set it up. Well, the answer comes out to be not very pretty, but I will just tell you the answer. And yes, when you take the final exam, I will provide all the integrals for you. Relax. Okay, whatever, it's some function of n. And now let's compute sigma x. Remember, standard deviation equals the square root of this minus this, right? Plug and chug. Let's plug away. Okay, square root of L squared times 1/3 minus 1 over 2 n squared pi squared. Right, so that's just taking this result. Minus the square of the average, L squared over 4. Ugly. We can clean it up. We can take the L outside. And inside we get 1 over 12 minus 1 over 2 n squared pi squared. Well, now I want to plot this. What do you expect? What do you think the result will be? Well, you see the ground state, it's kind of clumped around the center. But the higher and higher excited states we just discussed, they look more and more like this. So they get broader and broader. But it can never be infinitely broad because eventually it becomes basically a constant between 0 and L. You average out over all these variations, it goes to a classical regime. Okay? And the classical distribution being a constant, 1 over L, you can also calculate the standard deviation there. We will do that. But it's not infinite. So let's see. When I plot this versus n, you should always, when you think about things, plotting is a really good idea. So here is n equals 1, 2, 3, 4. When you plug n equals 1, you're going to get about 0.18. Okay. And eventually, when n goes to infinity, how do you guys take limits? They taught you all kinds of confusing information. Well, what does it mean n goes to infinity? When n is infinite, this whole term goes to 0. Okay, so eventually it goes to 1 over root 12, which is approximately 0.28. Okay, so that's the limit. And you know, you reach that limit, almost that limit fairly quickly. Okay, so it's something like that. It looks kind of like that. So as advertised, the standard deviation doesn't go to infinity, it goes to some finite value. And yes, it increases because the wave function broadens up. You start with this. The second one is a little bit broader. The third one is even broader. And eventually you go to a classical limit. Okay, so the sigma x approaches 1 over root 12 as n goes to infinity. This must be the classical value. Let's check. Again, you see, it's not a proof. I'm not asking you to prove anything to me. I just want to understand it. I want to see if I can extract some physical meaning from this. Okay, there's no sense. All these things about proofs, formulas, just take it in the trash and throw it away. Okay, that's all high school nonsense. Okay, it's not a proof. It's analysis. It's digestion. It's examination. It's digging. That's what I'm doing. Okay, so classically, we discussed that P of X is just 1 over L. We discussed in the previous lecture. So from there, you can calculate average value. You will see that it's L over 2. Try it. And then you can calculate this, and that's going to be L squared over 3. So classical equals L squared over 3 minus L squared over 4, taken square root, which comes out to be L. I'll go outside of the radical. And you rationalize that, that's 1 over 12 equals L over root 12. And here I forgot to say that this is P over L. I'm plotting P over L. So P equals L times this bunch of stuff. So P over L is this, right? So it's not P, it's P over L that I was plotting, right? And so classically, so quantum mechanically, the standard deviation goes to L over root 12, sorry, L over root 12. And we think that that's a classical result, and it is. Okay, so again, it shows that as you go to a higher and higher, more and more excited state, your result approaches the classical result.